Okay, so for our last video for today, we're going to introduce a new type of recommender system. And we're going to call this recommender system matrix factorization. It has kind of a scary sounding name, and it is going to be a little bit more complex than all the ones we've seen so far, but we'll see that it works quite well in practice with some additional modifications. So my goal in this video is to not answer every single question or completely tell the story of matrix factorization. My job in this video is to set up the big idea. And then in class, talk about how this works, how we learn it, and how this is actually effective. Okay? So we're going to frame our recommender system as a slightly different problem. So we're going to go back to our movie recommendations instead of product recommendations. Our goal is we want to predict movies or recommend movies using previous user ratings. So we're going to assume we have this explicit feedback that users have rated some movies, and we want to use those ratings to help predict which movies they might rate highly and maybe recommend those. So our input data will be a series of users and movies and their ratings for each movie. So I have a green user, and they watched the black movie and rated it 3. The green user watched the purple movie, rated 5. The green user watched the blue movie, rated it 2, and so on and so on. So we have a lot of user ratings, and our goal is to somehow use these ratings to make predictions about future user ratings. A big challenge about this, though, is that users have rated relatively few of the entire catalog. So it's very rare to have one user rate every single movie. And even without that extreme case, the people that do rate frequently, they're not really rating a large percentage. So there's a very, very sparse data problem. So what we'll do is we'll think about these user movie ratings as a matrix, showing which ratings we have so far. What I mean by that is we'll have rows for users and columns for movies, and every time a user rated a movie, we'll have an entry there for their rating. So this is a matrix showing the ratings for each user-movie pair. Now, the problem with this matrix, as I just said in this challenge, is there's a lot of missing entries because not every user has rated every movie or watched every movie. So we'll have a bunch of missing entries. And I'm showing a pictorial representation without numbers as this kind of matrix with black and white squares. Black squares being ones that the user has rated and give us a number, and the white ones are the ones without a rate. So all of the ratings will be numbers between 1 and 5. We'll just assume 1 to 5 stars. Each row here corresponds to a user, and each column here corresponds to a movie. Our black squares in this picture equals a known rating, and the white squares are unknown rating. I'll say white. Unknown rating. And commonly in this lecture, I'm going to use the symbol question mark to say I don't know what they rated it, because they just haven't rated it yet. So we're going to have some ratings and a lot of missing ratings. And we can frame the goal of our recommender system as trying to complete this matrix. That we have some information about some of the user moving ratings, and our goal is to go fill in all of these spots. And so on and so on. And if we fill them in, then we can use those predicted ratings to fuel our recommender system. Our goal is to use some of the values to predict what we think is likely for the other ratings. What do we think the user will predict for these movies based on what they've used before? And we're representing this matrix to kind of give us flexibility of looking at one user's ratings across all the movies, and look at, for each movie, the ratings from all the users that we'll talk about how we do that. Now, I'll mention right off the bat that this is a pretty ill-posed problem. What I mean by that is really there's an infinite number of rating sequences you could write down in the white squares because we don't know what those values are. So we have to make an assumption that there's some structure to this data that will help us predict with the given data what the unseen values are. And so the type of assumption we'll make is that because this problem is impossible without some assumption, the unknowns could really be anything, we're going to assume that there are K types of movies, and we're going to have to talk about how to pick K. So like action, romance, and different users have various interests in each of these categories. So we're going to assume that there are K categories of movies, and each movie can belong to, some combination of those categories, maybe half action, quarter romance, quarter mystery, or something like that. And we'll also assume that each user has some kind of fixed preference for each type of movie, for each category. Now, the way that this kind of assumption will unfold is that we're going to represent each movie, and I'm going to use the letter V for movie, with a feature vector, RV. And the notation here is going to look a little bit weird at first because it's going to fit into a broader framework. So you'll just have to trust me that this notation will make sense when we have everything together. It makes no sense right now why I would use the letter R or subscript V. We'll get there in a second. The idea is we're going to represent each movie with a feature vector, RV, and that's just going to represent how much this movie belongs to each of these K categories. So maybe it'll be something like 0.3 action, 0.01 romance, 1.5, and so on and so on. So this is going to be a vector, an array, with K numbers in it. This is notation to say it's a K number array. Those numbers are real numbers. We're not going to require any normalization, summing to 1, or anything like that. It's just showing us how much it belongs in kind of category. And again, I haven't told us how to learn this thing. That's going to be a huge part of this problem. I'm just setting up. My goal is to learn a K-dimensional feature vector for each movie that somehow corresponds to these kind of K categories that users are in. Additionally, the other thing we're going to try to learn is we're going to try to describe each user U with a feature vector LU. And that's going to be how much each user likes action, romance, drama. So for example, user LU, the feature vector we might learn, might say action, likes romance, likes mystery. Again, does not need to be normalized. It's just saying higher values mean that this user likes these things. Again, I haven't set up how to learn these, but this is our goal. Our goal is to learn a K-dimensional vector for the movies and a K-dimensional vector for the users. Each user will have their own vector. Each movie will have their own vector. And with this estimation task, our hope then is if we want to estimate the rating between user U and movie V, then we'll just do our kind of normal multiplication between these two vectors, doing that kind of element-wise product and summing them together. So here, I'm just taking 2.3 times 0.3 plus 0 times 0.1 plus 0.7 times 5, and this gives me a number. This number is my estimate for the rating. We call it rating hat, but we're going to use this notation UV to say, well, it's a function that takes a user and a movie and then predicts what that user's rating is. Actually, I don't like how that looks. And then our hope is to learn these movie vectors and learn these user vectors such that our predicted ratings are close to the observed ratings. So what we're trying to do is represent each movie in this kind of category space with K categories. We're also trying to represent each user in this category space about how much he or she likes those categories. And there's a whole host of learning problems that come with this. How do we actually learn this? Why are we representing it? Okay. But I want to show you an example to try and make this. So suppose we've already run our algorithm that I haven't described on a set of users and movies, and we found these features for the users and for the movies. So here what I'm using is I chose that K is equal to 2, that there are 2 types of movies, maybe action and romance. I'm not telling it exactly what those should mean. My hope is just by picking a number 2, it infers something. We'll sometimes call these user features and movie factors. And that terminology is a little bit weird. It just comes from this terminology of matrix factorization, which I think will make a little bit more sense in it. We'll sometimes call these factors. So each user, user 1, user 4, gets a 2-dimensional feature vector or factor. And then we have movie 1, movie 2, movie 3 that also gets its own 2-dimensional feature vector or factor. And what we're doing is we're learning these kind of representations for the users and the movies in this kind of low dimensional space where K is 2. So what we'll do is we'll represent all of the users in a matrix that we'll call L. And this matrix, in this example, is a 4x2 matrix. 4 being the number of rows, 2 being the number of columns, the number of columns being the number of factors. But in general, this is a 4 by K. Actually, I'll say N by K. N users, K factors. We'll learn an N by K user factor. And then for the movies, we'll call this matrix R. And in this example, it's a 3x2. But in general, it's an M by K. M movies, so M rows, and K factors for K columns. Each one of these rows represents LU, and in this, RV. And this is actually kind of where I get that notation L and R from. I'm talking about something on the left and something on the right. So I'm calling this matrix L and this for users and R for movies. And LU is the row for user U, and RV is the row for movie V. Okay, and you might be wondering, why the heck is this useful? Why is it useful to put all of these user vectors and movie vectors into 2 matrices? Well, the structure of this kind of learning algorithm and why it's called matrix factorization is we're going to do something called a matrix product. We're going to multiply 2 matrices. And this is something you'll learn in a linear algebra class. And this linear algebra is not a requirement, so we'll just quickly show you how to do this. And you can look up online if you want to see more examples. Matrix multiplication is just a procedure to multiply 2 matrices together that looks a little bit weird the first couple times you see it. What you do is you go for the left matrix row by row, and the second matrix column by column. So what you'll do is 2 times 3 plus 0 times 1. 0 times 1. That gives you a number 6, and you fill that in here. And then you move which column in the second matrix over by 1. Do 2 times 1 plus 0 times 2. That's 2. Move the column over. 2 times 2 is 4, plus 0 times 1 is 4. Then when you run out of columns, you go back to the beginning and move down a row. 1 times 3 is 3, plus 1 times 1 is 1. Add those together to get 4, and so on and so on and so on. We multiply all kind of pairs of rows and columns together, and we'll get numbers for all of these positions. Multiply the L and R matrix together to get a new matrix which will have a bunch of numbers in it. Now, importantly, we've done something kind of special here. Remember, I said that this L matrix will have number of rows n and number of columns k. And note something a bit weird here is I'm not using the matrix that I defined up here R. I'm transposing it. I'm flipping the rows and columns. So now it will have k rows, m columns. And now the final result will be an n by m. Now, if you haven't taken a linear algebra class, one thing to note is when you do this matrix multiplication, because you're going rows in the first, columns in the second, the number of columns in the first matrix and the number of rows in the second must match, which is why we have to do that transpose, make the k's go towards the. But then we get an n by m matrix. And now I can emphasize the importance of this learning. These numbers we're learning here are our predictions for the user's rating. So the entry here, maybe I'll pick the entry here at entry ij is going to be equal to our predicted rating for user I, movie J. What we're doing is we're trying to complete the whole matrix by choosing user factors and movie factors that when you multiply them together in this very special way, get a predicted set of ratings that are close to the ones that we actually have data for. So for example, if I actually have data for this one being 5, and maybe I'll write this in color. If I have data for this one being 5, and this one being 1, and this one being 4, and this one being 4, our goal is to find these numbers for L and R. When we product them together, give us predicted ratings that are close to the true ratings. But the power is that we can use all the other ratings to make predictions about the future, because we don't have those. So the reason this is learnable, or the reason we do this, is we're assuming that the users and movies have this low dimensional, where the number of dimensions is k, representation. Our hope is to learn this low dimensional representation for each users and movies, so when we multiply them together, give us back something that's close to the original ratings matrix that we have data for. So I think this slide will try to emphasize that a little bit more. So we have a bunch of filled in ratings, and our goal is to fill or learn two matrices, L and R transpose. R is going to have m rows and k columns. We transpose it together, such that when we multiply L and R transpose, we get something close to the original data. So our original data had n, and we learned this user factor with n users and k columns, and this R transpose with k rows, m columns. And again, transpose swaps rows and columns. Used to be m by k, but because we're transposing, it's k by m. Our goal is when we product them together, we get something close to the original matrix. So then our goal, our learning objective, is to find an L and R that when multiplied together, achieve predicted ratings that are close to the values we have data for. So our quality metric is actually going to be something like least squares. But the notation here is going to look a little bit different because we have a bunch of missing data. We're trying to find the settings for L and R, the user factors and movie factors, such that when you multiply them together, you get numbers that are close to the data we have. The way we write this out is as a sum over all ratings that aren't question marks. So this is over all ratings, UV, that is not equal to a question mark, actually. I'll zoom in here. So loop over all ratings that aren't a question mark, taking the prediction for row U in the user factors and row V in the movie factors, multiplying them together to get a predicted rating, subtracting away the real rating and squaring that error. So it's just squared error, but applied to our predictions for each user movie combo that we have data for. We get the predicted rating, then find the squared error. So here is our predicted value. Predicted rating for you. And this is the actual rating for UV. And this loop is just over all of the rows we have data for. For entries, we have data for. Now, the reason this ends up being a learnable or hopefully learnable thing is that if we just tried to fill in all of these numbers, there are a total of n times n total numbers, minus the ones we have values for. But that's a lot of values we have to learn. Generally, learning is more feasible if you decrease the number of parameters you have to learn or the number of values you have to learn. So in this representation where we learn these k-dimensional L and R user and movie factors, only numbers we have to learn are n times k user factors and m times k movie factors. And assuming that we choose k to not be too large, this will be a much smaller number, hopefully one that we can learn with the limited amount of data we have. I will mention, because this video is getting a little long, I want to wrap up, that this is not a completely well-posed problem. In fact, there are many solutions to this problem. For example, if you find one set of user factors and movie factors, that when multiplied together get you something close, there will then be an infinite number of solutions that get you the same accuracy. If you just scale up all of one matrix by some constant and decrease all of the other matrix by some other constant, so this is multiplying everything in L by 2 and dividing everything in R by 2, you'll end up with the exact same prediction. And so in fact, there are an infinite number of predictions for this that match up. The takeaway is that this is a useful tool for prediction, but a terrible tool for analysis. That you should not read much into this number being 3. That doesn't really mean anything on its own. It's all relative to everything else, because any kind of scaling of those numbers, as long as you scale correctly, will end up being correct. Okay, so there's probably still a lot of questions about this. Do not worry. We're going to try to answer all of them in class, particularly what algorithm do we use to find these kind of users and factors, and talking about kind of why this even works in the first place and some ways to prove it.